Right, there are of course no acoustic challenges, there are only acoustic problems, I was once told by a project manager who just had a very bad meeting with 3 separate acoustics consultants telling him 3 different things. But the good news really about TAB's classrooms and acoustics is that it's not as problematical or as challenging as we might have thought that it was, certainly easier than I thought it was when the first concept came in. So, what is a TAB's classroom anyway? TAB's thermally active building, effectively a room with a concrete roof or soffit. So we can't do what we would quite like to do with a traditional classroom, which is to put in this kind of acoustically absorbed ceiling, which is a problem because they work quite well. Now, why is this a problem? In fact, why are we concerned about acoustics in schools in the first instance? Well, the contractors in the room will of course know exactly why that is. It's because they've got a contract which says you must comply with BB93. There is incidentally a paragraph at the beginning of BB93 saying that the purpose of BB93 is not to be a contractual document, and any contract which says compliance for BB93 is not actually doing its job properly, but that's what we're lumbered with. And I remember disagreeing strongly with my colleague Andy Parking here a long time ago when he said the moment we write standards down, those will become the de facto standards and no one will ever think of any other kind of acoustic standards. And I told him that he was talking rubbish, and in fact he wasn't and I was. So we're stuck with it. BB93, we have standards. Those standards are going to become varied in the new revision of school premises regulations, independent school standards, in the priority schools building programs, specifications and so on. And arguably those standards are now being adopted as standards for fitness for purpose when there is a dispute about the acoustics of a given school. But we do have to remember that the reason why we have these standards in the first instance is because you need good acoustics in schools for them to work. Whatever transformational educational agendas you may have, whatever educational or educationalists may be telling us, we do still have most of our education being conveyed in the same way that I am trying to convey information today, by talking. You've got to be able to hear what I'm saying. The children in schools have got to be able to hear in much more difficult circumstances than this. And the difficult circumstances are, as a rule, 30 kids sitting in a room are not going to sit as quietly as you are because you're all nicely well-behaved adults. You've had a cup of coffee, and you have presumably turned up here because you want to be here rather than because your parents have kicked you out of the front door. Secondly, not very many of you have hearing impairment at the moment. Most kids actually have some degree of hearing impairment at some stage during their development. David Canning came up a while ago with the rather alarming figure that at any one stage between the ages of 8 and 18, about 25% of any children in a class have something which in an adult would be diagnosed as a hearing impairment. They might not know it, but they've got glue ear, they've got infections. The human ear doesn't actually form completely until the age of about 18 or 19, and so we can't necessarily judge acoustic conditions by our own standards. We have to be more fussy about schools than we would be about buildings for adults. So ultimately, whatever we do, we have to remember that we should be trying to achieve the best possible acoustics. And these are not the best possible acoustic standards. These are the minimum standards to be achieved in building regulations. They are the least that we have to do. Secondary classrooms, mid-frequency reverberation time of 0.8 seconds. I'm not going to go into the technicalities because most of them, you know them already, and besides, this is not a technical presentation. If anyone wants to go into exactly what a TMF is, then we can point you towards more technical papers later on. Primary classrooms generally are slightly smaller. Generally, primary children have lower distraction thresholds, effectively, and we look for lower reverberation times there, about 0.6 seconds. And the one which always catches everybody out is for hearing impaired or deaf children or children wearing cochlear implants or hearing aids and so on. We actually look for a much more stringent standard of 0.4 seconds, which is quite difficult to achieve in most classrooms, and perhaps in the current climate, more relevant, it's quite expensive to achieve. In specialist schools for hearing impaired and deaf children, we actually try to achieve the BATOD, British Association of Teachers for the Deaf standard, which actually has reverberation time control at low frequencies as well, which is not impossible to achieve, but it's very, very rarely achieved at the moment. Shane mentioned the Essex study a little bit earlier on, and there are some summaries scattered about the rooms for it. But basically, I'm mentioning it here just to give an idea of why we are getting so worked up about the acoustic aspects of things. Effectively, David Canning and his research team took 4 nominally identical classrooms and, by changing the acoustic absorption in the classrooms, achieved these 4 very different acoustic conditions there. That is not an easy thing to do. Achieving those bottom 2 curves there without actually making it very, very obvious that you just filled your classroom with acoustic absorption is actually, well, it required a certain amount of subtle thought and engineering, and was in itself quite an achievement. And the outcome of it, very simply, is that as the reverberation goes down, not only do the teachers and pupils enjoy the experience more, insofar as any kind of school might be considered enjoyable, but also the academic performance in terms of tests and so on seems to improve as well. And this is absolutely consistent with the very long-term studies done by Bridget Shield and Judy Dockrell and their team over many schools, effectively where you can show a clear relationship between good acoustics, lower reverberation times in schools, and better academic performance. Now, I came to this whole business assuming that not being able to put in an acoustically absorbent ceiling would actually cause us problems. But in fact, the traditional design of a school with a flat, very absorbent ceiling and no other acoustic absorption in it causes us several problems in the first instance. One of them is that we don't really know what sound absorption coefficients to use. Acoustic absorption coefficients, they're given to us quite often in nothing more helpful than a graph like that, in octave bands, and somebody's probably guessed what the value at 63 Hertz at the low frequencies on the far left hand side there is, because we don't normally test down to that, and that's tested in a laboratory. It's not unusual for a laboratory test to come back and tell you that you have an absorption coefficient of more than 1, in other words, that your acoustically absorbent material is absorbing more sound than is incident on it. That causes a few kind of major physical and intellectual problems. It's simply to do with the way the sample is put in the laboratory. Obviously doesn't happen in the real world. And it is a source of some concern to me that we still don't really have a standardized way of taking laboratory data and working out, well, okay, what should we really use on site for our calculations? As a general rule, I just multiply everything by about 0.85, but that's probably not something which I should advertise. The other thing is that in a typical classroom with the only acoustic absorption being on the ceiling, we get this very, very strange effect of what are known as room modes and flutter echoes between hard parallel walls. This is a rather extreme case from one of the examples that I'm going to show a bit later on. We had a school where there were some thermally exposed ceilings, concrete soffits, and some acoustically absorbent ceilings. And in one of these, my colleague Joe Bear went in and tested with and without furniture in the room. And without furniture in the room, he got the upper blue line there, reverberation times, mid-frequencies, getting on for about 0.9 seconds, which doesn't comply with any standard known to man. And the moment the furniture came in, it virtually halved. The reason for this is not the acoustic absorption of the furniture, it's acoustic diffusion. It's the fact that this actually effectively breaks up the sound field and means that more of the sound waves actually get diverted and impinge on the acoustic absorption in your ceiling. That it itself is an effect which we knew about in sports halls and in, say, particularly tall rooms, but this actually happened in a fairly standard size and shape of classroom. So the traditional design of classroom already brings a certain amount of uncertainty and confusion with it, and one thing which has been exercising the minds of the BB93 revision committee is simply how do we go about testing somewhere. We would like to test in rooms as they are actually used, which is with all the furniture and with 30 kids in there. In practice, this doesn't normally work, and the contractor wants us to do a test before the furniture even goes in because he wants to get his completion certificate and get off site. And so I can see in future it's quite possible that there will be a standardised set of furniture which will be put into rooms so that we can do the acoustic absorption, and I will walk around the school with a sound level meter and a bloke with a trolley full of furniture will be following me. If only. This is quite an interesting example, and you'll be relieved to know that from here on in it's basically all examples. This is a special educational needs wing to a school in Chatham, and it's designed about 3 years ago. It's not a TABS school because it actually has timber panelled ceilings. Why it has timber panelled ceilings, to be perfectly honest, I don't know. I think that the architect and the client just thought they looked really cool. They certainly cost enough. But timber ceilings, effectively acoustically reflective. We weren't allowed to put any absorption at all up, in fact, on these ceilings. And actually one of the reasons given for that was that there are quite a number of children quite high up on the autistic spectrum in this school, and there's quite a lot of discussion about how easily distracted they are by any regular patterns, linear effects and so on. But looking at that, I can see a fair number of linear patterns and distracting things in there anyway. But never mind, we had to put in wall panels. Standard sized classroom, 44 square metres of wall panels went into this. That is not an easy thing to achieve, given that you've got to get them out of the way of children who naturally wanted to find out how easy it is to destroy an acoustically absorbent wall panel. And in this case the wall panels are all at high level around the top of the classroom. You can see there are, and coming all the way down one wall on one side. I haven't been back to the school recently to find out whether they're still there and undamaged. But the good news is that actually it complied. The even better news is that the commissioning data that we have from it, which is not produced here because actually we only got the measurements very, very recently for this one, as in about 6 o'clock yesterday evening, actually is slightly lower than the predicted data, which is always nice because there's always a certain amount of uncertainty about these things. But yes, effectively coming in around about 0.6 seconds. Not brilliant, but okay. Now, the great advantage of the TABS classroom is that we can actually put some absorption up at ceiling level or just below ceiling level, and typically there'll be the kind of suspended units which Ecophon have very helpfully put down at the far end of the room there, so that you can see what they look like, absorbent rafts effectively, and I'm sure Pedro will tell us how many of them we're allowed to have in a room without completely fouling up the acoustic performance. I hope so, because that's the only reason I came here anyway. This was part of the Building Schools for the Future project in Lewisham, and this was in fact for a school for primarily for autistic children, but Lewisham, in an unusually enlightened moment for any kind of education authority, said, well, we want to design these to the standards for hearing impaired children because we know that many autistic children are exceedingly upset about noise. We did quite a bit of research about acoustic criteria for this one. Also, because quite a lot of autistic children also have hearing impairment problems, so let's get the best acoustics that we possibly can in these rooms. And of course we start out the place where every decent acoustic consultant starts out with, which is you do a 3D acoustic model of the space and try to locate your acoustic absorption as accurately as possible. As you would expect, we've got acoustically absorbent rafts being modelled in this room here, covering about 40% of the ceiling area, which seems to be a reasonably standard figure for the amount of absorption that the mechanical ventilation engineers will allow us to put into a room, and the rest made up of high-level wall panels. Now, technical difficulty here is how do you actually model the acoustic absorption of something which is hanging below the ceiling? In theory, you might think, well, you're getting twice the amount of acoustic absorption because you have absorption on the underside and on the top of the material. In practice, that doesn't seem to work, and in the past we had effectively taken a kind of fudge factor and say, well, okay, we'll multiply it by about 1.5 to get to overcome the fact that not all of the sound actually impinges on the upper side, on the back of these absorbers. But for this job, actually, one of my staff did some reverse engineering from previous jobs to work out whether or not he could find an empirical relationship between the effective acoustic absorption in this type of room and the absorption coefficient that you would measure in a laboratory. And we found that the best way of doing it was, in fact, to model the front of the absorption as effectively something approaching the laboratory data there. So the bottom line you see there, ABS raft front, is the definition in our computer program of the front or the underside of the acoustically absorbent raft, and that's got figures going up to about 95. You'll see we don't try to tie these things down to 1 or 2% because it's not worth it, it's not that accurate. So, plus or minus 5% we reckon is pretty good in these cases. And then the reverse side of this, oh look, it looks as if it's about, at most frequencies, around about 50% of that. So it's a pretty good indication, in fact, of the idea we had first was about right, but effectively what Lawrence, my colleague, was doing was adjusting the acoustic absorption of the back of the raft to achieve the reverberation times which we had measured on site, and we could compare the measured and calculated results for these things. That seems to work reasonably well. I'm considering selling the data to Echofon. And it works. In this case, we went in, we have measured acoustic absorption in the rooms with furniture. In this case, we model the rooms with furniture because I think it's entirely reasonable to assume that no child will be being taught in a room which doesn't have some furniture in it. We have 3 different types of acoustic prediction using different algorithms within our CAT modelling program, and 2 of these actually also tie up with what you would get if you were just to do the calculation using the traditional Sabine method, which assumes that you have a reasonably even distribution of absorption around the room. And within 10-15% they work. That's okay. And the really nice thing is that the measured one sits right down the middle of all of those figures. So people say to me acoustics is not a precise science. That's absolutely true. We do have to allow ourselves plus or minus 5%, roughly speaking, we think, on acoustic absorption calculations in these rooms. And I can also guarantee that if I went back into exactly the same room the following day and re-measured exactly the same thing, I'd end up with very slightly different results. But it is that accurate. We can reliably predict that for a certain geometry we can make it work, not just to achieve the normal standards, but the hearing impaired standards as well. Broadwaters. Welcome to Broadwaters, it says at the entrance, which is always a nice thing to see when you go to a new school. I don't know how many of you will admit to being old enough to remember the Broadwater Farm riots many years ago in North London. This is an extremely impressive building on the site of the Broadwater Farm estate, and bless them, they've kept the same name. They've never tried to pretend that it's anywhere else. But a rather lovely building designed by Gollifer Langston Architects, and I'm very grateful to Adam Wood of Gollifer Langston for providing me with these photographs. Another school with a lot of special educational needs provision in it, and in particular PMLD, Profound Multiple Learning Difficulty classrooms. My colleague Joe Bear worked very closely with Adam in integrating the acoustic and the architectural design together in this. It's a lovely building. PMLD classrooms are difficult because, for a start, they're bigger than standard classrooms, and one thing we do all know about reverberation time is as the volume goes up, the for a given amount of acoustic absorption, the reverberation time will go up as well. And in an ideal world, of course, your acoustic criterion would be volume related, but you can't really find a way of writing that into regulations. Also, quite a large area of floor in a PLMD classroom tends to be vinyl, acoustically hard. You don't get the benefit of the carpet. And also it has got to be pretty much bomb-proof, because with the best will in the world, quite a lot of these children are, at one stage or another, quite disturbed, and it's not unusual for them to get to the disturbed point at which they start throwing things around, and if you have soft materials on the walls, they get damaged. So it's quite a challenge to start out with, and what we've ended up with here is acoustically absorbent rafts underneath the ceiling, 280 millimeters down, I think, and again they cover, I think it's about 45% of the ceilings in this case, and the rather tasteful light blue turquoise colour around the top there is acoustically absorbent wall panels at high level, again out of reach. And I have to say, when I first saw this, I did ask Joe to do some fairly detailed computer modelling of it, because it looked a bit optimistic to me. But in fact, the reverberation times come out absolutely spot on. There's one room, you'll see down there, fourth from the bottom, the Year 4 Key Stage 2 room, where the reverberation time is a little bit over the 0.4 second TMF criterion we were looking for. The reason for that one is that it's in fact measured without any furniture in it. We were commissioning at quite an early stage in there. But all the other rooms absolutely on the nail, and I'm confident that with the furniture in it, the Key Stage 2 room would also do that. So okay, it's done, it's possible. TAF classrooms, acoustic absorption, it works. So I don't really need to say anything else, do I? However, I think I'm going to be required to, because Shane doesn't want me to finish until 10 past. So let's just expand the scope a little bit, because this whole philosophy of having thermal control through exposed soffits and thermal heat sinks, for want of a better term, of course works very well in other types of buildings. And a type of building which seems to be a growth area at the moment is the University Library. I know of quite a few that are being built at present. This one is the University of East London Library in Stratford, which rather supplements the UEL Library in Docklands, which is one of the great acoustic disasters of all time. The main reason we were dragged into this is because the Docklands Library has so many acoustic issues with it, not the fault of the acoustics consultant, because there wasn't one, that the client really wanted us to sort out with Hopkins Architects at the outset what acoustic criteria should we aim for, how can you define those in an open plan building to start with, how can you measure them, and how can we achieve them. The UEL Library is quite an interesting building, but it's a fairly standard layout these days, so effectively the central part of the library is all open plan with bookshelves in it. We still have books in libraries in spite of everything that we were told 15 years ago that they would just be laptops and workstations and so on. Books in libraries are good news because they're acoustically actually surprisingly absorbent. They have the almost inevitable atrium area, although this case you'll see that here we have a set of trees in a small atrium which actually links the three levels of the library together. So it's all effectively open plan, but not to the stage at which you have a big enough opening for the sound actually to reverberate around the entire building in a big way. And we have, along the side walls, we have quiet or silent study areas where people will sit, and in the open plan quiet study areas people talk quietly. In the closed rooms, with you see the partitions and various folding partitions, in these closed rooms people are basically required to sit quietly and not make any noise at all. And it seems to work. But a critical part of the brief, and not open for any kind of negotiation, was that all of the concrete soffits throughout had to be exposed. This is great news for an acoustics consultant because it means we get to build a really complicated computer model, and don't they look great? And of course the more detail we put into them, the more impressive the computer model looks, and don't tell anyone, but the less well they work. We generally find if you overdo the detail, the edge effects start to become a bit of a complication, and also very small acoustically absorbent surfaces don't actually work terribly well at low frequencies. These are ray tracing programs, and so there's a certain amount of interpolation to be done. And there's a a good deal of experience is required to actually work out with these programs what to model and what not to model. But anyway, this was great fun, and it took Joe about 2 weeks to put it together. And it took the contractors about 2 years to put it together, and they actually did a rather good job of it. The job has just been handed over, slightly delayed by a bit of a flood on site because somebody managed to cut through the water main about 3 days before acoustic commissioning. So it's the only occasion on which I've had to commission a building whilst wearing welly boots. And the acoustic criteria throughout the building were set actually in the open plan areas in terms of the transmission of sound. Effectively, you put a loudspeaker at one point, how much of the sound has actually been absorbed, how much of it's going to transmit as well to somebody 10 metres further down the building. Because if I'm in an open plan library, I don't want to hear the conversation that's going on down the building. This is much more reliable and useful than a reverberation time criterion in an open plan space because, first of all, RT varies enormously as you go around an open plan space. And secondly, we don't really use our ears to detect reverberation in that particular way. What we detect is how much we can hear of what somebody's saying. And we found that a surprisingly small amount of acoustic absorption suspended from the ceilings worked in these areas. By surprisingly small, we're talking about around about 25% of the ceiling area, which is still an awful lot of acoustic absorption in a big building with 3 stories. But a lot of the absorption actually is provided by, well, carpets. Actually, surprisingly little of that comes from the carpets, especially at low frequencies. Furniture, fittings, books, desks and so on, they all do their bit. So the important message there is model with the furniture and fittings in the building. You wouldn't expect this to work really because there is no acoustic absorption in this room visible from the furniture. All we've got is a bit of carpet and about 30% of the ceiling space being covered by these suspended panels here. I should probably point out that these suspended panels, I may be drummed out of the building for this, they're not made by Ecofoam. And the reason I'm pointing that out is because they're not actually as absorbent as the ones made by Ecofoam. They're basically put in because the architects thought they looked really good, and they do. But yeah, okay, we have to balance the aesthetic against the acoustic effects of this, and actually it would have been possible to do this one with about 22% of the soffit area covered, and it works again, absolutely on the nail as far as the acoustic commissioning was concerned. And again, this slide here gives you some kind of idea of how little of the ceiling area has to be covered by these things. We haven't yet found a way of using the device which of course all architects would like to use, which is a very slightly absorbent light fitting to do it. You don't have enough area in your light fittings to give you sufficient acoustic absorption in a case like this, but it's a pretty good indication. We're going to write this one up properly. It will be on our website, and we'll probably bore the Institute of Acoustics with a presentation on the subject. It's a standard hazard of the Institute of Acoustics. You go to conferences and you hear the equivalent of what I did in my holidays with all of the papers. Look, we've done a job and it worked. But that one was interesting enough to do. The nice things were that without particularly over-designing, without completely blowing the acoustic budget, in fact we didn't spend all the acoustics budget at all, we actually came in at comfortably below the reverberation criterion, which were all based on Building Bulletin 93. It's a further education building, so we didn't have to achieve it, but it was a good standard to aim for. As you look at the bottom 2 lines on there, the noise decay in the open plan areas did pretty well what we would expect. Over short distances we get about 6 dB per doubling of distance, which is a kind of free field acoustic condition, and over longer distances we were getting coming down to 4 to 5 dB loss with doubling of distance, which again is an indication of a fairly well controlled acoustic environment. We also had the option, although not adopted in an awful lot of places, we could have specified acoustically absorbent, not bookends really, but library shelf ends. We've used these in other places, including the Forum Library in Norwich, which was the first of the big acoustically controlled open plan libraries. They are surprisingly effective as well. In the places where we have used these on one floor, you can tell the difference in the acoustics, but to be perfectly honest, in my view, I don't really think that they're worth the hassle. They're quite expensive to produce. They don't look so pretty, and I can guarantee that when I go back, I will find loads and loads of little bits of paper that have been stuffed into them by students who clearly have nothing better to do than to stuff little bits of paper into small holes. So, in conclusion, it works. What's all the fuss? In my experience, TABS classrooms actually work better than the conventional design with a flat acoustically absorbent ceiling. The reason for that is simply we're getting the acoustic absorption further down in the room where the people are, we're providing more diffusion in the room, and we're providing a room which is actually coming a little bit closer to what Wallace Sabine said when he shouted Eureka, or Mother, it's a hyperbola, or whatever he shouted, when he realised that in fact you could predict the amount of the reverberation time from the amount of acoustic absorption in a room, provided that it's reasonably evenly distributed. We do have to think about practical absorption coefficients. There's still more research to go into this. I remember 25 years ago when I first started doing these kind of calculations, the first question I went to ask to the people who knew all the answers were, what's the practical absorption coefficient? And roughly speaking, they said, oh, take the lab data and multiply by about 0.9. We haven't progressed very far from there. We really do need to do some more work on this. We need to do more acoustic commissioning in buildings for two reasons. One is that if we don't, people won't bother with the design, or they will bother with the design and not actually install the materials, or they will do it wrong. And the vast majority of jobs where we go back, where acoustic commissioning hasn't been carried out, we find problems because in the absence of acoustic commissioning, nobody bothers too much about it. And also, as well as being a compliance check, acoustic commissioning and sharing the information that we get from sites and from this commissioning actually allows us as acousticians to do a better job for the rest of the world. So I'm all in favour of as much commissioning as possible, not just because we earn more money from it, but because it does actually give us the chance of getting things right and producing more acoustically efficient designs in the future. So I hope that in 2 years back here, 2 years we'll be back here, and I shall be prattling on about the possibilities of reducing the amount of acoustic absorption in TABS rooms, simply because we now know exactly what a practical acoustic absorption coefficient is, or maybe one of my fellow speakers will be able to talk about that a little bit later on. Right, that's it.